In this video, I'm going to take a used discarded Makita battery and turn it into a 6S1P pack for my long-range drone. These Makita batteries contain 10 high-quality 1865 zero cells. In 90% of cases, the cells are in perfect condition. It's the battery's electronics that fail, causing them to be thrown away. I've previously built a 6S2P battery and a single-pack battery. Now, I'm making another single-pack battery, which I'll be using in parallel with the first one I made. The Makita battery is assembled with 4 tamper-proof Torx screws, so you'll need a Torx screwdriver with a hole in the center. I believe it's called a security Torx. On one of the screws there's a rubber seal to make sure people don't open the battery. In a moment I'll show you a clever trick to remove it. To remove the rubber seal, take a fairly large wood screw and drill it into the rubber. Use a pair of pliers to pull the screw back out, and just like that, the rubber seal is removed. At this point, it's important to point out that working with batteries can be dangerous. There's a reason why Makita batteries are well sealed. This video is only a demonstration of how I do it. If you choose to do it yourself, it's at your own risk. The Makita battery is originally built as an 18-volt 5S2P battery, and it contains 10 cells. There are also 2 screws inside the pack that we need to remove. After that, I use a side cutter plier to remove the nickel plate from the cells. Be careful here not to short circuit the connections between the cells. If that happens, sparks can occur, and in the worst case, the cells could explode. Have a plan in place for what to do with the battery if that happens. Before removing the final part, it's a good idea to place a piece of electrical tape to minimize the chance of a short circuit. Now go ahead and do the same with the other side. To remove the electronics, loosen 2 small screws and then break it off. This part won't be used again, and it's most likely defective anyway. pack contains Sony VTC6 cells. They have a capacity of 3000 mAh and a max current draw of 30 amps. In a 6S2P configuration, this results in 60 amps max current draw and 6000 mAh, which is suitable for cruising with a long-range drone. I'm now going to test the cells to make sure they all have over 2.5 volts. If I find any that are below that, I'll assume they are defective. In addition to checking the voltage of the cells, you should also run a capacity test. This can be done using an 18650 cell test. I'll include a link to it in the description. All the cells had 3.78 volts and are perfectly balanced. So it's clear that the electronics have failed in this battery pack, not the cells. The last thing I do before I'm ready to start building my battery pack is to prepare the cells. I cut away any leftover nickel plates with a side cutter and then lightly sand the surface. This helps the solder to stick properly. After that, I wipe the batteries with IPA to clean them. The manufacturer recommends using a spot welder and nickel strips to assemble the cells. I don't have a spot welder, but as long as you're careful with the heat, soldering the cells together has worked fine for me without damaging them. Now that all 6 cells I need for this battery pack are ready, I can move on to the next step. To connect the cells, I've made small jumper wires. These are 14 AWG silicone wires, cut to about 20 mm in length, with the ends pre-tinned for easier soldering. For a 6S battery, you'll need 5 of these. You also need 2 wires, about 10 cm long, for the XT60 connector, along with the XT60 connector itself to attach at the end. In addition, you'll need some heat shrink, Kapton tape and electrical tape to add some protection to the battery. I use a piece of thin foam padding. These often come with batteries or flight controllers when you buy them. You also need a good soldering iron. I use the TS101 with a C4 tip. It's thick enough to heat up the battery terminal quickly, ensuring a strong solder joint without the heat spreading to the rest of the cell. The next thing I do is glue the cells together in pairs. These are oriented in opposite directions. To align them correctly, I use a 3D printed jig. I do this with all 6 cells, ensuring that each pair is oriented in opposite directions. Before soldering the jumper wires, I pre-tin the cells. Use a lot of solder to make it easier when connecting the jumper wires. Here in Norway, we don't have access to leaded solder, which makes the process a bit more challenging. When I solder on flight controllers and ESCs, I use no-lead flux pens. For the 18,650 cells, no-lead flux isn't as important, and I prefer to use Amtech flux, which I find works better. One of the things I like about my soldering iron is that it can be powered both via USB and, for example, a 6S battery. I'll add a link to it in the description in case anyone is interested. When I solder battery packs, I set the soldering iron to 400 degrees Celsius. I do the same for the rest of the pairs. Make sure to solder all the connections on one end first, then move on to the first connection on the other end. This helps prevent the batteries from overheating. As you can see, when you do it this way, the batteries don't get much hotter than 36 degrees Celsius, or about 97 degrees Fahrenheit. Now I solder the jumper wires on one side of the pair first. Make sure to use a pair of tweezers or something to hold them in place while doing this, as they can get quite hot.
Don't think you got me figured out just 'cause I tell the truth. I got you all figured out by your lights.
Now the three pairs will be put together to form a battery pack. It's important to keep in mind that all the cells should be connected in series without creating a loop. To make it easier, you could draw the direction of the current flow on the batteries and where the XT60 connector should be soldered. Before I solder the rest of the jumper wires, I glue the cells together with hot glue in the order they should be. Again, I use electrical tape to cover the poles so that I don't accidentally short them while soldering. Now you should get about 22 volts on the negative and positive terminals of the battery, depending on how fully charged they are. The last thing to be soldered is the balance cable. It is used for balance charging the battery pack, ensuring that the cells do not go out of balance. But before I do that, I clean up the battery a bit with IPA and a toothbrush. As you can see, I don't get the shiny round solder joints that you get when using leaded solder, but not too bad anyway. I almost forgot the XT60 connector. I prefer to solder this on before the balance cable. I always solder the connector itself first, then solder the cable to the battery. This way, it doesn't accidentally touch anything and cause a short circuit. Since the XT60 connector tends to get so hot that it melts, I use a short stopper as a heat sink. This way, some of the heat is dissipated. I like to put a couple of heat shrinks on the inner part of the XT60 connector, in addition to the cover that comes with it. I made it a bit longer than I normally would, since this one will be used together with another pack on the same drone. Finally, there's the balance cable. It's probably the most stressful part since there are so many wires. I try to make it fit between the XT60 wires so that it comes out on the same side of the battery. The balance wire usually has a red wire, and the rest are black. I typically start with the wire furthest away from the red one. This one goes on the negative terminal of the 6S pack. Then I work my way inward toward the red, which eventually goes to the positive terminal. After the first black wire is soldered to the main negative terminal, you skip one cell from the main negative terminal and continue like that. It's less complicated than it sounds. When I'm done with the balance cable, I like to run a test on the charger to check if it reads all the cells correctly. If you see a crazy high voltage on one of the cells, you've most likely soldered something wrong. You can see in post that it's hard to see the display on the charger, but I'm putting up a picture on the screen now. As you can see, it shows all the cells with the correct voltage. Finally, before the battery pack is complete, it needs to be protected and wrapped. It's important to wrap and insulate the battery pack before it's fully assembled to ensure durability and safety, especially in high impact environments like FPV drones. I start with a layer of Kapton tape to cover the ends of the cells. Kapton tape is a heat resistant, electrically insulating tape made from polyimide film. In FPV drones and battery packs, it's often used to secure and protect wiring, insulate connections, and add an extra layer of protection without adding much weight. Then I add a layer of this foam padding over the ends of the cells on both sides of the battery. This helps absorb impact in case of hard crashes. As I mentioned, this is often included when you buy batteries or flight controllers as a protection in the box. Cut it to the size you need and tape it securely in place with electrical tape. After I've attached the foam padding, I tape the rest of the battery as well. Finally, I wrap the battery pack in heat shrink. Ideally, for 18650 batteries assembled this way, you should use 95mm wrap. Unfortunately, I only have 125mm wrap, so it's a bit large, but it will work. I make sure to cut out a small section at the top for the XT60 wire. I'm lacking a proper heat gun. I use my daughter's hairdryer to heat the heat shrink. As you can see, it sticks out a bit at the corners because the heat shrink isn't ideal in size. But if you bend it down while it's still warm, it works just fine anyway. I apply a bit of hot glue between the XT60 wire and the balancing wire to provide some stress relief and make them more durable. Now the battery pack is finished and ready to use. Building a battery pack this way is very cost effective, as you're only paying for the accessories you need. To get used Makita batteries, you can contact your local recycling center or Makita dealers. They often have a stockpile of defective batteries they are required to take in, which they may end up discarding. Many of the packs I've opened look almost unused. It seems like there might be a weakness in the electronics of some of these batteries. You can also use other brands than Makita. In a DeWalt pack I opened, there were 21,700 cells, which is even better. Thanks for watching. Please give me a thumbs up and subscribe if you liked the video.